This is the first example on the transient portion of the course. This circuit is a first-order circuit, and we call first-order circuit any circuit that has one storage element, here a capacitor. Of course, it could also be an inductor. The basic idea of a first-order circuit is that when you solve that circuit, you're going to end up with a first-order differential equation, an ordinary differential equation with constant coefficients. When we look at a circuit like that, and you have a switch that opens up at t equals 0, it is implicit that this switch has been, in other words, the connection has been here for a very, very long time, and at t equals 0, it opens up, and the part of the circuit on the left where the current source is becomes disconnected from the part on the right. Now, anytime you have a switch, you ought to know that we solve the circuit for the time period before the switch action, which is before t equals 0, and the time period after the switch action. We never solve the circuit at t equals 0 because it's undefined. So in the case if we had two switches, we would have three time periods. So we begin by solving the circuit for t less than 0 seconds. We have to solve the circuit sequentially. We can't solve the circuit for t greater than 0 first and then for t less than 0. And the reason for that is because we need the solution for t less than 0 as initial condition for the solution for t greater than 0. Now, in this problem, you are asked to calculate the voltage VB across that 1 ohm resistor. Even though you are not asked to calculate the voltage across the capacitor, here that I call VC, you have to do that. The capacitor voltage is the initial condition. If you had an inductor, it would be the inductor current. So, and the reason for that is because the energy in a capacitor is equal to 1/2 times the capacitance times the voltage across the capacitor squared. And we are guaranteed that the voltage across the capacitor is always continuous. In other words, you never see jump in the voltage across the capacitor because the energy cannot be changed instantaneously. So now I put my polarity like I do, but you can choose your polarity, but the bottom line is that you have to calculate the voltage across the capacitor. The second thing is, for the time period for t less than 0, the circuit has been a DC circuit for a very, very long time. So the capacitor behaves like an open circuit. So you virtually replace the capacitor by an open circuit. So in this case, we basically have a DC circuit to solve by using either mesh or nodal. And we need the two parameters we need here are VB, of course you asked to calculate that, and VC, the capacitor voltage. So I decided to set up a nodal analysis procedure. We could have easily set up a mesh. It's no different here. So we have 3 nodes in addition to the reference node, which I pick at the bottom. And the top node here, I call it VC because obviously it is VC minus the reference node. We have a supernode, which I'm showing in green here because of that dependent voltage source. And we are going to seek to calculate VC, V2, and V1. I put my currents and what have you. First step is we write the voltage source in terms of the node voltages. So VC minus V2 equals 4IA. That's our first equation. Of course, we'll later on write IA using Ohm's law in terms of the node voltages as well. The other 2 equations, they're going to come from a KCL at V1 and the KCL at the supernode. KCL at V1. V1 is a regular node. In other words, it's not the reference node and it's not a part of a supernode. So we basically, it's a regular node and we write the KCL about it. Current coming in equal current coming out, or the sum of the current equal to 0. We do the same thing about the supernode, and when we do that, of course, we consider the supernode as a big dot and write the KCL about it, and you have it at the bottom of the screen. We're going a bit fast in this problem because I'm assuming that by now you can solve a DC problem using mesh or nodal without any problem. Next, we write the current in terms of the node voltages by ways of Ohm's law, and of course, IA is just simply V1 divided by 2 using Ohm's law. And then we're going to use this equation in the 3 equations, that is the 2 KCL and the source equations, and then we're going to solve for the node voltages. These are the three equations, three unknown, the unknowns being V1, V2, and Vc. And then solving them, what we really need is, well, we need Vc and V1 because Vb is Vc minus V1, and also, of course, we need Vc. So we get Vc equal 15.25 volt and Vb being 6.775 volt, about 6.78. Now, the value of Vc being 15.25 is going to be our initial condition at t equals 0 when we solve the circuit for t greater than 0. Now, this is the part of the circuit that is the most interesting part, because obviously our interest here is to learn how to deal with the transient response of first-order circuit here. So the switch has opened up, so the left part of the circuit is no longer present. Folks, anytime you have a circuit that you're trying to calculate the transient response, I want you to focus first on finding the ordinary differential equation for that circuit. Here it's going to be a first-order differential equation. Now, once we do that, the solution to that is going to be fairly straightforward. But the first goal here is to come up with that differential equation, and we do this by doing basic mesh or nodal. Now, we're going to do mesh or nodal just like we were doing for a DC circuit, and we're going to slightly tinker around to bring in the capacitor equation. Of course, for t greater than 0, you can see that the capacitor is back, because now you had a change at t equals 0, the capacitor now behaves like a real capacitor. Notice also that my Vc polarity has to be the same as the previous time period. Okay, so I go ahead and set up a mesh. There is nothing different here. I put my two mesh currents. Of course, you can clearly see that I1 is equal to IA here. And I put the voltage label and polarities on the resistors that didn't have any voltage defined. In the case of, for example, the 1 ohm on top, I already had VB, so I'm not going to go ahead and add another one. Now we have two meshes in this case, two meshes, and none of them contain a current source. So we're going to go ahead and do KVL equations in both meshes. The top one is for mesh I1, and the bottom one is for mesh I2. There's nothing dramatic, nothing important about these KVL. Two regular KVL, and I'm going to suggest again, folks, particularly for the transient discussion, that you do your KVL in terms of voltage and you do your KCL in terms of current, because really things get a little bit more complicated because we're going to be dealing with differential equation in that part of the course. So we go ahead here and write our KVL. We're going to do Ohm's law for resistors. Of course, there is only Ohm's law for resistors, nothing else. So we write V1, V2, and VB in terms of the mesh currents by virtue of Ohm's law, and of course, IA is equal to I1. Okay. So at this point here, nothing has changed. All we've done essentially is what we've been doing for a DC circuit. Now, what I want you to do is take those Ohm's law equations and stick them in your true KVL. In other words, for the time being, forget about the capacitor. Let's work with the resistors. We'll deal with the capacitor a little later. So we take those Ohm's law equations and we physically put them in our two KVL equations. You see, I haven't touched the capacitor. I'm still having Vc in there, and that's no problem. Now, the next step I'm going to do is collect terms and and then have in terms of Vc, I1, and I2. So we collect terms, and we have our two equations. Now they have the capacitor voltage, I1 and I2. At this point, we haven't done anything that you haven't done before, and I'm expecting that all of you can get to that point without any errors. Now we're going to handle the capacitor. We say that the current through the capacitor is minus, which is I1 here, is minus 0.1 times the derivative of the voltage versus time. It is minus because the current, the way I have it, is entering the negative terminal, so it's against the passive sign convention. Remember, capacitors and inductors are also passive elements, so that's the reason it's minus. So what am I going to do here? I am going to take that equation, And wherever in those two KVL equations I have I1, I'm going to replace it by minus 0.1 dVc dt. Here we are. So these are the same equation, except now I1 is no longer present because it's been replaced by minus 0.1 dVc dt. Now this is a point where sometimes students get stuck and get a little bit confused here. So we've essentially eliminated one unknown, I1, and we have these two equations. What I'm going to do next is solve for I2 in the bottom equation. I'm going to solve for I2, and when I do that, it's going to be I2 is equal to minus 0.8 dVc dt divided by 5. And then I'm going to use that result for I2 in the top equation. Now, I could have solved for I2 also in the top equation. I could have done that, but I elected to do the bottom one because it appears to be simpler. But the idea is to use this equation and substitute so that we come up with one equation, and it's going to be a differential equation. So the end result is the differential equation, which is the first order that we have on the screen. Now, the next thing that I did is normalize that differential equation. It is traditional to normalize the differential equation such that the coefficient that is associated with the highest order derivative, here there's only a first order, is 1. So I just divide by that and you get the differential equation in the traditional form. Because we're going to be talking about how do we solve such differential equation, such form of differential equation. And the next slide will deal with that. This is a very good general slide because it tells you pretty much how to handle any case relating to first order circuits. You have a first order differential equation with constant coefficient alpha. Alpha is a constant, and it's equal to a constant k. Now, in our case, k is 0. But when we do step responses, k will be maybe 10 or 5, some kind of numbers. So this is a very general and an excellent slide. And that's the point that I make about I want to see the differential equation. That's going to be the gateway for a fair amount of credit. Because in my view, I'm not trying to teach you differential equation here, but once you come up with the differential equation, I expect you to be able to write the solution just like I have here for that example. Of course, in this case, k is equal to 0, so the only part that we have is the a e to the minus alpha t, and in our case, alpha is 2.78. So the solution is Vc for t, and again, that is for t greater than 0, is equal to a constant a e to the minus 2.78 times t. Now, where does a come from? It comes from the initial condition on the voltage across the capacitor at t equals 0. So what do? We say Vc at t equals 0 must be equal to the previous value of that voltage across that capacitor at t equals 0 minus, in other words, right before the switch opened. So A is equal to 15.25, which is the value of the capacitor voltage at t equals 0. Having done that, then we can solve for I2 using one of the KVL equations some time back. And of course, if we know I2, VB is simply 1 ohms times I2, and then we can essentially our problem is solved. I'd like to recap a little bit here before we finish, because this process that we see is the standard process for solving the transient responses of circuits. What we do, we start with either mesh or nodal, just like we've done before. And then, if we're doing, for example, in the case we're doing mesh, we go ahead and write KVL equations in each mesh. Of course, depending if we have current sources or not, we may have to do super mesh. But we proceed the same way that we've been proceeding for DC circuit. The second step is that we write Ohm's law equation for all resistors. And we use these Ohm's law equations into the KVL and other equations. So we do all that just like if we have a DC circuit. Now, we handle either the capacitor or the inductor now after that. So we go ahead and write a voltage-current relationship for a capacitor or an inductor. If it's a capacitor, it's the current to the capacitor is C times dV dt, V being the voltage across the capacitor. If it's the inductor, it's going to be the voltage across the inductor is equal to L times di dt, where I being the current through the inductor. Then we bring those equations, you bring that either that capacitor or inductor equation into those KVL equations that we have. And then the rest is essentially manipulating and substituting to come up with one differential equation.